So here I have the tetrahedron, and I've chosen staple strands in red. Each edge is a bundle in honeycomb lattice. So here's the honeycomb, and we can switch this to strands. And if we look closely, we can see where crossovers are. So for example, here, if we put those as red, it connects this helices to this helices. Looks like it's a staple strand, not the scaffold. So this is a bundle because all of these helices are connected to each other. Each crossover can only be made at certain points along the helix. Obviously, from, let's say, this crossover, which goes to this above helices, is a certain distance apart. Likely from here to here, it is about some integer number multiplied by 10.5, right? Because it needs to make a full turn from here to here. It's not exact, but it's pretty close. It's also connected down here. Which is at some other angle, which is some other distance. And if we take a look at the path panel, remember this is the cross-section or slice panel. This is the path panel. And then this is aux view, looking at the entire structure, atoms, bonds, and everything. 3D. CAD Nano's 3D sort of sucks because it needs to be transferred to the path panel, so it doesn't look good. Anyways, again, we have different types of helices. So we examine this bundle. They're all connected to each other with staples or with the scaffold itself through holiday junctions. And we have two inner helices on this honeycomb bundle. The two inner helices point towards the interior of the tetrahedron. If I zoom out, you can see that there are two inner helices that point towards the inner tetrahedron. And this is for all bundles. So if you look at this bundle up here, there are two inner helices that point inner to the inner of the tetrahedron, and likewise here there are two helices that point towards the interior of the tetrahedron. And these two interior, we can call them interior helices. The two interior helices determines our essentially, because this structure hasn't been optimized, but after optimization, these bonds are definitely not this long. But after the optimization, through Talos, we can use the interior helices to determine the interior volume or the size of our tetrahedron, because we don't really care about the exterior as much as the interior, because we need to fit a nanoparticle inside, right? So these are just example demonstrations of staples here, but they would come from the interior helices because they face the interior. There are two exterior helices that act as the very edge of each side of the tetrahedron. So these two point to the exterior, these two point to the interior. Notice that the interior is shorter and the exterior is longer, basically because when this thing closes to make its tetrahedral structure, you're going to need some shorter helixes to fit the interior and the exterior to be longer, so that the vertices or whatever they call mitred as opposed to flat. Anyways, these can be identified in CAD Nano. So first of all, the slice panel will tell us that the program that Talos uses to generate this in CAD Nano, it always gives us this form. It makes each bundle separately. It's a tetrahedron, so there are 6 sides, so there are 6 bundles. So in the view diagram, you can look at each strand, and the colors are not that great, but the scaffold strand, let me select strand. The scaffold strand is one single strand, so if I just click it properly, it will give me the entire scaffold, which is routed throughout this DNA origami nanostructure. Staples are all the other ones, and they run out of colors just like we always do, because there's whatever 200 staples, so they'll just alternate between this dark color and this grayer color and a beige color. You see a beige color here. Anyways, so let's take that view off. Back to my point was the two smaller interior helices can be found on CAD Nano. Basically, you have to determine which one of these is the small, and you can just count, right? So helices 1, I guess I'm going to take this panel out, but helices 0, 1, 2, 3, so 0, 1, 2, 3, so we have, if you're trying to determine which one of these is the smaller one, obviously you just count how many bases there are. And so if you look at 0, 1, 2, 3, and 4 and 5, which is the first bundle, you will see that there is a scaffold. Don't include these here, but base pairs begin when you see 2 parallel lines from the staple, which is green or red, and the scaffold blue. So if you count the number of bases pairs along here, and along here, along here, along here, you'll see that the 2 short interior helices in this bundle is this one and this one. There should be 42 total across. That is the parameter I gave it when I submitted to Talos. I don't have Talos out. So when you submit this to Talos, I chose with tetrahedron, right? And I chose 42. This is the minimum edge length of my structure, and I guess they use that as the parameter to spit out the algorithm, so that the algorithm could spit out the product, whatever. So that's why there are 42 along this shortest edge, which, if you recall what I was saying, it's these two guys. And each edge has obviously two of those. So and we want to choose the staple to be in there, obviously. So now the arrowhead points towards the 5 end, so we need the arrowhead. I've labeled them as, or I've colored them as purple. It's just a staple now, but this purple staple is going to be the capture strand. They are working in the room next to me, so there's going to be a rattling noise. Whatever. Anyways, so this staple here is a little bit complicated. There's plenty of base pairing occurring here before the staple comes off to become a capture strand. So the overhang I am not including here. So right now it's just considered a staple. So interior helices in the bundle here. Purple strand is capture strand. There's a lot of unpaired bases here. That's good because if you look at the tetrahedron, and right now I have, let's go ahead and select strand. So let's go ahead and select. Okay, so purple, or the selected strand, is the scaffold strand. And what I'm trying to show you here is that when this helix joins to this helix here after optimizations, so this helix and this, what we need to know is let me think here. These extra bases that are unpaired, they need to be unpaired because there's no way one helix can join another helix without because DNA is rigid and it wants to generally be it generally doesn't want to fold upon itself, and so you have these base pairs that are unpaired because it needs room to bend. Because single-stranded DNA is quite flexible compared to double-stranded DNA, and even more rigid is an entire bundle. Anyway, so that's why there are these extra base pairs that are unpaired on the path panel, as you can see here. Even the scaffold has an extra base that is not paired right here, which is interesting to know. So from going from one bundle to another bundle, you'll see that how the bundles connect to one to another is, if you look on its vertice, you'll see that the two exterior bundles will connect to the other two exterior bundles that are closest to it. So this, let's go ahead and view clusters. All right, so now we have this cluster, this cluster, this cluster, this cluster, this cluster, or edge we can call them, or bundle we can call them. But all I'm saying is the exterior bundles connect to the exterior bundles. The side bundles, or the side helices, connect. So the exterior helices in a bundle will connect to other exterior helices. So exterior helices combines with another exterior helices, and of course the nearest one. So this one is not gonna cross over to this one up here. This exterior is gonna cross over to this exterior, this one to this one. And so if you look at the path panel, you'll see that if we're looking at the exterior helices, which are these two long ones, this one and this one, you'll see that they go over to another bundle, right? In this, wherever that bundle might be. And it should connect with another exterior helices. So let's follow a staple instead of the scaffold. So this green one, it goes to 34. So it goes from here, I believe it's 3, 0, 0, 1, 2, 3, yeah. It goes from 3, which is an exterior helices, that's the long one, and it'll jump all the way to 27, which is another large or long helices. That's the exterior helices. And if you go follow it to 27, so green 27. Some people are talking.
Porque la chichita esa nomás entra al traste de abajo para detenerlo. Nomás es para que no se salgan.